If you remember, in the last class, we talked about a storekeeper managing an operation, serving a customer, potentially doing having a continuous production system. And essentially, the storekeeper orders an amount of inventory. There may be some demand fluctuation. When the inventory hits the reorder point, an order is placed, and the order arrives after a certain amount of time, which is the lead time, which may be fixed or variable. And at that point, the inventory position jumps up depending on the size of the order itself, which typically is the economic order quantity. The inventory again depletes. When it hits the reorder point, once again an order is placed, and again at some point the next shipment arrives, and so on. Now, when you're looking at this, what can you say in the previous class? What can you say about this time interval between any two orders? You know that when you hit the reorder point, you place an order, but what can you say about this time interval? What does it equal to? No, this time interval between any two orders?
It's constant.
Was it so? Okay, so let's say if you had no demand fluctuation, what would this reorder point be?
Constant.
Constant. What would it be equal to? Q by R, right? Remember that you ordered R over Q number of times. So every cycle actually is of the length Q by R. So if there are no demand fluctuations, the time interval between any two orders would be Q over R. Now this Q, how do you determine this Q? That's the EOQ, which is essentially nothing but a trade-off between the inventory holding cost and the ordering cost. So you made a trade-off between two different kinds of costs to actually come up with a Q, which then determines the time interval between number of orders and also the time interval between any two orders. That's when you have no demand fluctuation. When you throw in demand fluctuation, what's going to happen? It's going to vary more than that, right? It's not going to be fixed at Q by R. It's actually going to even start varying. And why is it going to vary? It really depends on the demand fluctuation itself. On some occasions, you hit the reorder point very quickly. On some occasions, you don't. It also depends on how much inventory is left over initially, right? And then, depending on how demand actually fluctuates, you hit the reorder point at different points in time. So on average, this interval was actually Q over R, which itself was a consequence of optimization. And now it's even going to fluctuate more beyond that, Q over R. It's going to fluctuate depending on the demand fluctuations themselves. All right? Okay, so that was what we observed in the last class. What can you say about the ordering cycles in this problem? Fixed, right? Why are they fixed? It's daily newspapers, so potentially here you're saying that customers actually don't have any value for this newspaper on the next day, so you have to turn it back to your supplier as scrap, right? At some price, you may get some value for it, but essentially it has no value for your customers per se. You'll have to give it back to the supplier himself, right? Okay. So as a result, you have to bring newspapers on a daily basis, even if there were an ordering cost. Because you're bringing this on a daily basis, so it's a regular ordering policy that's being forced on you because of the nature of the product category. Can you really do anything about the ordering costs themselves? Unlike in this example? No, right? Apart from trying to negotiate and reducing it down, in reality there is no, by your own operation you can't do any optimization on the ordering costs. The ordering costs are actually sunk in this case. Even if you were incurring ordering costs, because you are coming in on a daily basis, you have no choice. You have to order at those specific intervals. There's no choice. And as a result, even if you are incurring a cost, your entire ordering cost is really sunk. It's a fixed cost you may have to take into account in some cases, but it's sunk. You can't do really anything about it. Okay. Now, other instances where you can see the same thing is when the ordering cost essentially is negligible. There isn't much of an ordering cost at all. As a result, what happens as a result is that you end up following an ordering cycle that is, as per your convenience, based on the customer's requirements or some other convenience that you can think of, right? Some other constraint. So you're ordering at a particular cycle. It's a fixed ordering cycle. You're not really worried about changing this ordering cycle because you have nothing to change because these ordering costs are negligible. So either if the ordering costs are negligible, or if the ordering cost, or if the product is in a sense perishable, like in this case, under both instances, the ordering costs do not play any role in this, in sort of finding the optimal solution. And so that's one of the key differences between what we did the last time and what you're doing here is that there is no ordering cost to play with as such. Because in this case it's not relevant or it's too small and you don't worry about it, all right? So that's a big difference between what we did in the last class and what we're doing now. So which is there is no ordering cost to worry about. Instead, what's the trade-off you're going to make? Yeah? Right, so if you can't serve customers, you have a lost sale. So there's an opportunity cost of a lost sale here. And if you have, that's when you don't have enough inventory. If you have excess inventory, So I'll come to holding cost. Yeah, there could be a salvage cost. In this instance, what's happening is you're selling it back to the supplier. You're selling it back to the supplier, and the supplier is not willing to give you back this. It's not like a fully refundable sale back to the supplier. You're going to incur a loss on that. So that's your cost of having excess inventory. In some cases, so although I said there are no ordering costs here, in some cases holding costs might actually matter. In fact, the handouts themselves here have a problem that invokes the holding costs. I think somebody mentioned the holding costs here. And the reason the holding costs might sometimes matter is instead of selling it back to your supplier, sometimes what might actually happen is you have the liberty to carry it forward the next day, right? So the cost of overstocking is essentially the cost of holding it to the next day, essentially, right? In this case, you can't do it, newspaper, so you have to sell it back to the supplier. But in some other instances, the cost of overstocking might actually be the holding cost of holding it to the next period, essentially, right? So holding costs can indeed play a role even in this context. Whereas ordering costs now play absolutely no role because the ordering cycles are completely fixed, all right? Fair enough? Okay, so the trade-off is between the cost of understock and the cost of overstock. And clearly we have some intuition about it. And one of the reasons we need to do this is because demand itself is a random variable, so we need to worry about how to manage this random demand by stocking appropriately or ordering appropriately, right? Okay, so I'm going to illustrate this by using a simple demand distribution. So the demand distribution, so what kind of a demand distribution is this? Uniform. Well, a uniform is a continuous distribution. It is more of a discrete version of the uniform. So it's really a discrete distribution. If you think about how this distribution looks like, it's simply going to be, you have 5 different points. So you either sell 1, 2, 3, 4 or 5 quantities of newspapers on a particular day, and the probability values are 0.2 of each. I'm taking 0.2 each just to make it simple. Okay, and this is a demand distribution you're dealing with. There is variability, and you have to handle this variability. Right? Okay. Now, what I want to do is, you've probably already looked at this solution to this problem before in DMOP, where you actually had to do the simulation. I'm going to build the logic here, and as usual, to build the logic, I'm going to sort of just experiment a little bit with the numbers. So, in the sense, let's do a little bit of not trial and error per se, but let's do some brute force calculations. Once you've done that, we have some intuition about what the solution is about, and then we can sort of try to derive the formula for that. All right? So that's going to be the objective. So what I'm going to do is, we know that demand is a uniform distribution with these 5 values, and the associated probabilities are as follows. And what I'm going to do is, I'm going to start off with, experiment with, I'm going to bring 1 newspaper. So this is my ordering quantity, 1 newspaper, right? And what we can also do is, we can calculate the understock and overstock under different demand scenarios. Okay. Now let's say I bring in just 1 newspaper, that's my ordering quantity. There are different possible demand scenarios. If the demand happens to be 1, what's my understock and overstock? 0, 0, right? When its demand is 2, what's my understock and overstock? Understock is 1, right? Because if demand is 2, I still have only 1 newspaper with me, which means I can't make a sale to 1 customer. So my understock is 1, my overstock is 0. Here it's going to be 2, 0, 3, 0, and 4, 0, right? Okay. Now, what I'm going to try to do is, if this is the ordering quantity, we don't know whether this is optimal or not. So let's try to see if we can change this. So clearly moving downwards is of no consequence, because if I go down, it's going to just be 0. And if I'm going to order 0, I'm going to make no money. So obviously that's not the point I'm looking for. What I'm really looking for is somewhere where I can make money, but more than what I'm making currently. So essentially, I'll try to move from Q equal to 1 to Q equal to 2. So let's try Q equal to 2, right? So if I bring Q equal to 2, I can redo these calculations. The probability stays the same. Okay, so if I bring 2 newspapers, my demand is just 1. What's my understock and overstock? 0 and 1, right? So there's no understock, but now I have an overstock of 1. If the demand is 2, then 0, 0, then 1, 0, 2, 0, 3, 0. Okay. All right. So if I were to answer the question, of should I move from Q equal to 1 to Q equal to 2, the answer is going to be given by marginal benefit, marginal cost. In fact, in this particular instance, because these different demand scenarios occur probabilistically, you let us start talking about expected marginal benefit and expected marginal cost. That's going to be a calculation now, right? So we'll have to do an expected value calculation. So let's first think about marginal benefit. By moving from Q equal to 1 to Q equal to 2, what did you gain? An excess sale, okay? Does it happen all the time? No. When does it happen? Only when demand is either 2 or 3 or 4 or 5. Because in each of these instances, what happened to your understock? It went down by how much?
1.
Exactly 1. Under each scenario, it went down by exactly 1, right? Fair enough? So which means that's your marginal benefit of moving from Q equal to 1 to Q equal to 2. And essentially, how would you calculate the expected benefit? You would simply say, so under each demand scenario, which occurs the probability of 0.2, 0.2, 0.2, 0.2, you gained exactly 1 sale because your understock went down by 1, right? So you're calculating your expected increase in sales, right? So it's 0.2 times 1 plus 0.2 times 1 plus 0.2 times 1 plus 0.2 times 1. Now the reason I'm writing it this way is it's for a reason. Even if I were to change these probabilities, let's say these were not 0.2, if this were 0.3, 0.4 and 0.1 for instance, right? This calculation would still hold, right? This calculation would still hold. You would just change those numbers. That's pretty much it, okay? The second thing is that under each of these probabilistic instances, your change or your benefit in terms of a sale is exactly equal to 1, right? That is not going to change irrespective of what these probability numbers are, because that really depends on the fact that you changed from Q equal to 1 to 2. That changes what is reflected in this extra sale that you're getting under each of these instances, okay? All right? Which means that I don't actually have to look at it this way. What I can actually do is, in all the scenarios where I gained, I know I gained exactly 1 extra sale, which means what I can do is, the probability of making an extra sale of 1 sale is all the probabilities occurring here, right? So I can just add them up, right? So I don't even have to do an expected value calculation. All I can do is I can add up all the probabilities. Because under each of these scenarios, even if these probabilities were different, even if this was 0.3, 0.4, 0.1, something like that, I could simply have added them up, because under each instance I'm going to make only 1 extra sale, alright? Only 1 extra sale. So I can just cumulate these probabilities, so I'm going to do exactly that here. So it's 0.2 plus 0.2 plus 0.2 plus 0.2, which is 0.8, right? So if I wanted to calculate my expected marginal benefit, with a 80% chance, I'm going to make 1 extra sale, right? 1 extra sale. And of course, this is on, I have not yet monetized this. If I were to convert this into monetary values, what would this be? On each sale, what is the margin that I make? 45, because I sell it at 70 and when I buy it at, well, I sell it at 75 and I buy it at 30. So I make a margin of 45. So my expected marginal benefit then is 0.8 times 1 times 45, which is, what is the value? 36. Okay, that's my expected marginal benefit. Okay, fair enough?